Urban areas are threatened by a whole range of extraordinary events resulting from a combination of natural, technological, social, and cultural risks. Some of these events can be prevented, while the negative impacts of others can be mitigated by technical and organizational measures. These measures can be preventive or repressive in nature. The typical documents in which repressive measures are defined are collectively referred to as security plans. This presentation will focus on a group of measures aimed at preventing negative events in urban areas, i.e., minimizing the number of negative events and reducing their potential impact. The presentation is entitled The Relationship Between Urban Growth, Exposure to Risks, and Vulnerability. Its content can be divided into 5 main sections. First, the learning objectives will be defined. Since a uniform interpretation of certain terms is necessary for understanding the issue, the basic terms will be defined in the second section of the presentation. The third part will deal with risks in urban areas and their types, followed by a presentation of ways to reduce them. The last part will present examples of events that have had a significant impact on urban areas. The presentation aims to familiarize listeners with the main risks affecting and threatening urban areas. As mentioned earlier, a uniform understanding of basic concepts is essential to understanding the issue. The second objective of the presentation is therefore not only to introduce the definitions of the most basic concepts, but also to explain their internal relationships and potential impacts. The final educational objective is to present possible procedures for conducting risk analysis in an urban environment. The most basic terms include risk and vulnerability. Risks are defined e.g. on the QualitySO website. Risk refers to the possibility of experiencing negative outcomes in uncertain situations. In the context of large, extraordinary situations, it encompasses various factors that can lead to significant adverse effects. These factors include the probability of occurrence per unit of time, uncertainty in terms of the effects and consequences of the event, and the impact on objectives with the possibility of quantification. Vulnerability, i.e. susceptibility to damage, can be defined simply as the average value of personal vulnerability and territorial vulnerability. In the case of personal vulnerability, the known population or the estimated number of people present in the area at the time of the event can be used. If necessary, population density can also be used. The technical vulnerability of an area can be calculated based on the predominant nature of land use, industrial production, housing, agriculture, forested terrain, water area, etc. In general, the higher the degree of urbanization, the higher the vulnerability of the area. Another option is to determine vulnerability based on the vulnerability of property, the environment, and infrastructure. The International Organization for Standardization, ISO, defines risk as the effect of uncertainty on objectives, which can be both positive and negative. In terms of the source of risk, a distinction can be made between natural risks, e.g. risks from natural events such as earthquakes, floods, or hurricanes. In the case of this type of risk, the most serious risks to urban areas include large-scale fires caused by technical faults, human error, but also drought and prolonged heat. Other very significant risks include earthquakes affecting large areas, floods and torrential rains, strong winds, tornadoes and other extreme weather events. However, biological risks, i.e. the possibility of the spread of infectious diseases and the emergence of pandemics, e.g. COVID-19, epizootics, e.g. rabies, or infectious plant diseases, also belong to the risks of a natural nature. Technological and infrastructural risks, sometimes referred to as operational risks, are risks arising from failures in processes, systems, or people, e.g. industrial accidents, collapses of energy networks and sewage systems or water supply systems. This category also includes risks associated with transport and transport networks. Here, risks can be divided into those associated with large numbers of private cars, but also public transport, rail transport, and lorry transport. In addition to natural hazards and technological and infrastructural risks, risks associated with urban complexes also include social and socio-pathological risks and financial risks. Social and socio-pathological risks are risks associated with human society and interpersonal relationships. A distinction can be made between social risks associated with unintentional and intentional activities. Typical examples include large gatherings of people, such as festivals or markets, and, on the other hand, vandalism, graffiti, or terrorism. In the case of financial risks, there are, for example, risks related to economic downturn or market volatility, which result in the demise of companies, rising unemployment, but are also associated with a reduction in public budgetary resources. Reputational risks are among the most significant and yet least researched risks. These are risks associated with damage to the reputation of an urban area or part thereof, leading to a decline in interest in living or doing business in the area and, in extreme cases, to the economic collapse of the area. Examples include the city of Detroit in the USA and, today, Pripyat in Ukraine. Finally, marginal but increasingly common risks in urban areas may be associated with modern construction work on buildings. These mainly include poorly executed renovations, unprofessional interventions in historical structures, or new buildings that disrupt the stability of surrounding structures. The problem with urban development can be defined as a triangle of urbanization and risks. The individual phenomena in this triangle reinforce each other. Rapid urbanization often increases the exposure of residents to danger, and if it is not managed, it also increases their vulnerability. In practice, urbanization means two characteristic phenomena. The first is the spatial expansion of urban areas. This involves the development of surrounding areas that were originally used only for economic purposes, fields, meadows, or were considered unusable for various reasons, slopes, river valleys, or coastlines. The second category includes places where there is a direct threat of landslides, floods, or where the ground is unstable due to erosion. In other words, these are places where the occurrence of extraordinary events is only a matter of time and not just a theoretical possibility. The phenomenon accompanying urbanization is population growth and, consequently, population density. In both cases, the larger number of people increases the demand for housing. However, population growth is not necessarily linked only to birth rates, but also to immigration from rural areas or, within the country and from abroad. The population curve can therefore grow very steeply. Behind the construction of housing lies the provision of energy, water, sewage systems, supplies, education, work, etc. These are further spatial demands associated with population growth. In order to work with risks, it is necessary to identify and quantify them. Experts have developed a number of methods for performing risk analysis in urban environments, but from the perspective of urban planning, it is only necessary to know the relationship between the individual components of risk in the area. Which risks increase and which, on the contrary, contribute to its reduction. These relationships are best illustrated by the following mathematical equation. The risk in the area is composed of the frequency of events, sometimes the probability of occurrence is used, which can range from events occurring every few years to only theoretically possible, multiplied by the expected consequences. The consequences are assessed in terms of their impact on human health and life, their impact on the environment and property, and the estimated time needed to remedy the consequences of the event. Sometimes this product is replaced by the term hazard. The result is then multiplied by vulnerability, i.e., susceptibility to damage, which can be simplified as the average value of personal vulnerability and territorial vulnerability. The last value in the formula is preparedness, i.e., the ability of the territory to mitigate the consequences of emergencies. In an urban environment, this will primarily include determining the level of preparedness, availability, and quality of emergency services, primarily the police, fire department, and medical services, means of protecting the population, and carrying out rescue and cleanup work. If we only consider risk as the source of the resulting damage, the equation will not be complete. The second factor that significantly influences the resulting damage is vulnerability, i.e., the susceptibility of an area, building, to the impacts of extraordinary events and crisis situations. Vulnerability is a relative value that allows us to compare the impact of the same event on two areas, objects, and the damage caused by this standard event. Vulnerability is influenced by a number of factors, in particular geographical location and type of development. This is also related to the standard atmospheric conditions prevailing in a given location. The resilience of buildings in the event of a hazardous chemical spill will vary significantly between areas with different temperatures and insulation requirements from external atmospheric influences. Another factor is the density and structure of the population, not only in terms of age, but also social and property status, especially the existence of informal settlements, such as slums. A very important aspect is the state of infrastructure. Overloaded and poorly maintained networks fail more quickly in disasters, causing power, sewage, and transportation outages, etc. Due to the combination of high exposure and high vulnerability, even relatively stable risks cause greater damage, and disasters are more serious. This phenomenon can be prevented by planned urbanization. There is a well-thought-out spatial plan, flood zone regulations, and houses are built to resilient standards. This means that urban planners resist pressure from developers to build in cheap, often risky locations. However, it is important to note that urbanization itself does not pose a risk. It acts as a multiplier of impacts, i.e., it increases the damage that occurs in an emergency. Thanks to new development, people are moving to places that were previously considered dangerous. For example, if flooding occurred in the past, the damage was significantly lower because the flood areas were uninhabited. The solution is therefore planned urbanization and well-thought-out zoning plans. Although new risk reduction measures are now being put in place, no one can rule out the possibility of negative phenomena occurring. Secondary risks must also be taken into account here. These arise as a consequence of primary damage. Damage to power lines leads to damage in surrounding areas, and the same applies to other infrastructure elements. However, the impacts can also spread to other areas, such as industry, education, public administration, etc. This phenomenon is generally referred to as increasing exposure, i.e., the impact of events that occur. Here, too, it is possible to eliminate these negative impacts. In this case, it is a sensible system of regulations governing the use of endangered zones, for example, the need to use more resistant technology in construction in view of the impending event. From a safety perspective, it is essential that infrastructure is modernized and correctly dimensioned in terms of capacity. In historic centers, infrastructure is often old and difficult to access. There must be a clear social policy that prevents the concentration of poverty in high-risk areas. In this way, the city prevents the emergence of excluded areas that can lead to the concentration of risks, e.g., in the event of a pandemic. And the development of the urban complex respects known climate changes that increase the frequency of negative events, e.g., floods, heat waves. Green infrastructure, retention systems, cooling areas, etc. are being actively and thoughtfully built. This generally means that urban planners are resisting pressure from developers to build in cheap, often risky locations. The ability to maintain the functionality of an area in the event of various negative events while adapting and transforming is generally referred to as resilience. A high-quality document on urban resilience is Resilient Cities_methodology.pdf, published by the Future Investment Initiative Institute. In this work, the authors use a system of indices to assess the level of critical infrastructure as a means of overcoming crises and define the level of maturity of critical infrastructure only in selected areas. In addition to the above methodology, a number of other published methods can of course be used to assess the level of resilience. An example is the City Resilience Index or the Holistic Index Framework for Assessing City Resilience, published by Marta Suarez. Also worth mentioning is the Global Risks Report 2025, published by the World Economic Forum. However, for quick orientation, a simpler method such as MindMap, which visualizes the individual connections between specific consequences and the probability of their occurrence, is often sufficient. The possibility of most consequences of extraordinary events can be documented using examples from the past. As examples can be floods in Spain, 2024. A rare atmospheric phenomenon known as a cold drop caused devastating floods in Spain. Lasting from October 29 to November 16, these floods brought extraordinary rainfall, dumping more than a full year's worth of water in just hours. The Valencia region suffered the most from Spain's 2024 natural disaster, receiving over 12 inches, 300 millimeters, of rain in just a few hours. Tragically, the flooding claimed at least 224 lives, becoming one of the most tragic natural disasters in Spain's recent history. One other example is the earthquake in Turkey and Syria in 2025. On February 6, a 7.8 magnitude earthquake struck southeastern Turkey, near the border with Syria, with its epicenter 37 kilometers northwest of Gaziantep. A few hours later, the situation worsened with a 7.5 magnitude aftershock and several smaller earthquakes. An area of approximately 350,000 square kilometers was severely damaged. The already desperate humanitarian situation in Syria was further exacerbated by this natural disaster. Over 55,000 people died in the earthquake. An example of a completely different type of event is the tornado that struck southern Moravia in the Czech Republic in 2021. In terms of strength, it was an F4 tornado, with damage and impacts affecting entire villages, which is an exceptional event in Central Europe. The closest comparable events are the tornado in Haute-Mont, France, 2008, and several historical tornadoes in Hungary and Germany. The tornado in the Czech Republic had a path length of approximately 26 kilometers and a width of up to 700 meters. It was the most destructive extreme storm with a tornado in the modern history of the Czech Republic and one of the strongest in Europe in the last decade. It destroyed or seriously damaged hundreds of houses, schools, offices, churches, and public buildings, power lines, and roads. It claimed 6 lives and injured over 200 people. However, there are many examples of significant destructive events. These include the terrorist attacks on the World Trade Center in New York on September 11, 2001, the terrorist bombings in Madrid in 2004, the extreme floods in Central Europe in 2002 and 2013, storms, large-scale urban fires, and industrial chemical accidents. A modern-day specter is a widespread blackout, which would mean the collapse of urban society. And from recent times, we can also mention the COVID-19 pandemic. Urban environments face diverse and interconnected risks. These risks arise from natural, technological, social, and cultural causes. Identifying specific risks, analyzing them, and analyzing their likely impacts is a fundamental task of public authorities and emergency services. Based on the results of the analysis, these units are equipped and trained. In the case of administrative authorities, contingency plans are drawn up to coordinate large-scale rescue and cleanup operations. For the most extensive events, individual countries also have a system of states of emergency in place, the purpose of which is to enable temporary adjustments to the legal framework and financial flows so that the situation can be dealt with more effectively and quickly. The number of individual states of emergency ranges from 2 to 4. The level of resilience and preparedness not only of urban areas but of all entities in general can be influenced by identifying the risks that threaten them and the vulnerabilities of individual parts. A whole range of methods, from very simple to complex and detailed, can be used to quickly identify risks, quantify them, and provide an overview. For easy orientation, the results of the assessment can be presented in the form of a risk map. Based on the overview obtained in this way, it is then possible to focus on specific identified areas and target the elimination of risks or increase resilience.